to the diffracting object. So everything that we've done so far has been this so-called far field or Fraunhofer diffraction, where we've got plane waves arriving at an aperture and we put our detector so far away, we've got plane waves arriving at the detector. And these actually are Fresnel diffraction patterns that are shown in figure 5. They are just facts. And how do we explain them? Well, first of all, just to remind you, again, I'm sorry, if this is a bit of a boring recap, but I think it's worth, being absolutely clear that to have the Fraunhofer diffraction, you've got to both have plane waves coming in and plane waves going out from the source. Now, of course, at the source itself, and we haven't made much of this. In fact, it's one of the view graphs that I've hardly used at all. This is called the Huygens construction, but it's part of what's called the Huygens Fornell, same guy, principle, that you can always find the propagation of a wave by considering every point on an existing wavefront to be a source of secondary wavelets. So this source sort of produces, of course, a kind of spherical wave, and this source produces a spherical wave, and this source produces a spherical wave, and so on. But, when you actually do the superposition of them, you just see, in the end, the whole wavefront, which started as this solid line here, ending up as this dotted line. And there is actually a degree of subtlety in this principle. And if you want to go deeper into optics, as I say, in Hecht's book is the one that I recommend. And he looks more at this Huygens Fornell principle. And which sort of been underlying everything that we've done, but we've kind of taken it, on intuition, on trust, that that's the case. And indeed, we used the whole idea when we were doing single slit diffraction of thinking, well, we've solved diffraction from n sources, where n is a large integer, there are loads of sources. And we said, well, we're going to consider a single slit as just a continuum of close-by sources. So we've kind of been using the principle all along. But now, clearly, if you're in the situation where either the source is close to the slit, and then, so these things are going to arrive not all, in other words, this sort of slit is not going to be all illuminated at the same time, because this bit of the wave arrives first and this arrives with a delay. So when you do Fresnel diffraction, you've got a different kind of problem. What I'm going to actually do is have plane waves incident on the slit so that they all arrive, but I'm going to have my detector close. So that also gives you Fresnel diffraction. It's an either-or situation, because even now all my, or if you like, all my oscillators, if I have the plane waves arriving, all these oscillators are driven in phase at the source, but the distance to point P no longer varies linearly with the phase. And how does it vary? Well, let's have a look at that. So the way that we're going to treat the problem, and this is qualitative, don't worry too much, there's certainly nothing in the exam or in the coursework which involves you calculating Fresnel diffraction, though you should be familiar with the main ideas of it. So what you have now is your point P is actually, this is, if you like, the source. Maybe this is a kind of wall here and a plane wave has arrived, and we pick any point Q in the source. Well, the difference in phase from this point to this point, this distance, is, of course, we can draw an equidistant. So this now becomes a reference sphere, not a reference plane, because we're taking into account the curvature of the wavefront. So if I draw this across here, a reference sphere, well, in the spirit of how we calculated before, we're going to have, of course, a wave which will be I to the E, kx minus this type of thing. Again, strictly speaking, and we'll come to this more next week, this should be a k dot r here for a three-dimensional wave. But the same idea is that there's an I the phase is retarded from the point Q relative to, let's say, that's the origin, by a certain distance. And all we've got to do is calculate that distance, in principle, it sounds easy, as we go across the slit, and then add up all the waves, if you like, from all these imaginary infinitesimal sources. It's the same idea, but the geometry is different. And the geometry is illustrated, I think, in figure 77. And you can see, so let's say exactly we've got some point here on the wavefront. Well, clear, and we put our point P, we put our detector, we made it, the geometry as simple as possible by putting it right opposite the origin here. So this distance here, travelled by a wave from this point, is S. Now clearly I can say, well, this whole distance here, this is a right-angled triangle. This is the distance h from the centre of the slit to the point of the slit. And this would include, of course, up to the width, the full width of the slit here. Well, it's obvious that that distance, by Pythagoras' theorem, is s squared plus h squared square rooted. Yeah? Well, if we now apply Pythagoras' theorem, then we know that this, and we want to calculate this distance here, again, because I'm not going to actually test this, I'll just use the notes. So the difference in distance between the two strips D is this s squared plus h squared minus s. So it's referring to this, is that this distance here, the extra distance travelled, is the square root of s squared plus h squared minus s, because this, we subtract off this distance, we get this little extra distance here. Now again, it's a very straightforward binomial expansion, a plus b to the n. Here it's s squared plus h squared to the half, gives us s plus a half h squared over s. Now again, we're going to say if, this is an approximation, but we're assuming it's a narrow slit, so h is very small. Even though our detector is now relatively close, it's still small compared with this little extra distance that's been travelled. We can use the binomial expansion, and so if I truncate the expansion here and I subtract s, the extra distance travelled by the wave at this point W in figure here. So this little extra distance that's been travelled by the wave in the Fresnel diffraction limit, you'll see goes as the square of h. So everything that we did before, we had the so there was our incoming plane wave, and then we had a great big screen that blocked most of the wave off. But we had our detector, so that we've effectively gone back to plane waves here, so we could draw a reference plane across here, and the phase, either from this point, obviously, let's assume this is all uniformly illuminated. Well, this has travelled an extra distance, and this has travelled a lesser distance. That's how we were doing it, but the extra distance was varying linearly as we went across the slit. Yeah? But now, when we're considering Fresnel diffraction, the extra distance that's travelled, this phase difference, of course, remember again, here's our old friend 2 pi x over lambda. This is my 2 pi over lambda is my k vector, and this is the extra distance travelled. The phase is varying. So Fraunhofer, it varies linearly. That's what we've done, and that's precisely what leads to that lovely simple, well, you might not think it's simple at this stage, but it's to a Fourier transform. And so you can solve the whole of Fraunhofer diffraction with Fourier transforms. With Fresnel diffraction, it's varying quadratically. So we've got a more difficult problem to solve. So so I put the answer up at the beginning. And of course, you can solve this problem by the phasor method. And now the phasor method kind of comes into its own, because calculating this diagram, the Cornu spiral, is actually quite difficult. I'll come to that in a minute. But you can, again, if you're good with Python or whatever, just start off at some point in the plane and start drawing arrows such that, of course, you won't get a perfectly smooth curve, such that the distance is just varying quadratically, and just you will see that you produce this amazing curve that winds round. It's not quite like an Archimedean spiral, but it's quite similar to an Archimedean spiral. Now, the way to interpret this figure, and as I say, you won't be asked sort of exam stuff on this, but I think it's kind of nice to know how people, it's like Fresnel diffraction is perfectly understandable. It's just a bit more difficult to understand. So the idea of this is that I wish I brought a ruler now. I'll go use the edge of this box. That'll do me. If you join Z to Z prime, yeah, so let's do it. Let's join Z to Z prime. That represents when there's no screen present. Now, the problem that I'm solving here, you won't believe how easy it is. So I'll say even the shadow formed by a straight edge is not straightforward. To calculate in the near-field regime. And again, I'm using entirely near-field and Fresnel as just synonyms for each other. You'll see both used, Fresnel diffraction, near-field diffraction. So what's being illustrated here is what happens when I just send light past a block. So in other words, I just am sending a huge, and remember we can consider the incoming to be plane wave if our detector's close, and I just literally am sending light through the lecture theatre. This is opaque and this is transparent. So in other words, I just send light past an enormous great wall. That's all that I'm doing in the physics of this situation, and it's very surprising. Again, I'll go to, in a sense, the answer, because that might actually make it easier to do the interpretation. This is what happens. So remember, just sorry, keep whizzing view graphs on and off here. All that I'm doing here, this might show better if I go down with the lighting. This is the situation of a straight edge. Well, obviously, if I had ray optics, geometrical optics, light travelling in straight lines, I just get literally a sharp edge. And exactly behind the great big wall, it's all black, and where there's no wall, it's all white. It's just very straightforward in geometric optics. But you'll see the diffraction pattern. Now, the Fresnel diffraction pattern next to the wall is actually surprisingly detailed and has got lots of little maxima and minima. This dotted line here corresponds to the edge of the geometric shadow. And of course, if you're a long way behind the barn door, it goes black eventually. These oscillations die out and you do get into a geometric shadow. And of course, if you go far enough away from the edge of the barn door this way, it's all light. And it must tend eventually, if I've got an enormous plane wave, I just get the amplitude of the plane wave, because it doesn't know there's a barn door over there cutting off some of the wavefront down there. But the actual intensity oscillations are surprisingly complicated. And you see the edge of the geometric shadow, actually the intensity of the light that gets passed at the edge is only a quarter the intensity in the incoming wave. There's a peak that goes up to 1.34, a first dip. This is intensity, this is irradiance here. This is the square of the amplitude that's been plotted. And you'll see loads of small fringes. And with modern photon detectors, you can actually pick up dozens, even hundreds of these small fringes. If you are unfortunate enough ever to have somebody like put an enormous searchlight on you, you will actually see your shadow will have a kind of ghost outer shadow on it. I don't know if you've ever notice that. But our eyes are kind of, if you like, sensitive enough to pick up occasionally with a bright source the first bump. Or you could look at it the other way round. Exactly. I mean, at the moment, you know, if I put my hand in shadow, you know, it doesn't just form a geometric shadow. This light's probably not quite bright enough to see the first minimum. You actually can see a sort of ghost shadow around your hand. Now, as you can imagine, this pattern with its hundreds of little oscillations here is not so easy to calculate. The way that this links with the Cornu's spiral is that again, you won't go into the details of exactly how the spiral's constructed. I'll mention it on the next view graph. You can do it, as I say, literally by varying the phase. Just keep drawing arrows, which instead of winding round a regular sort of figure like they did in linear diffraction, if the length increases with the square of the distance, they form this spiral. So if you've got no screen, and you join Z to Z prime, that is, if you like, gives you your initial A naught and therefore your I naught. So again, we're not doing absolute intensity. This is the intensity scale, is that length, Z, Z prime. So there's no screen. In other words, the whole plane wave just continues to travel forever. So, and that's what we're doing it relative to. We now drop the screen in place, then you join the origin O to Z, gives you the amplitude at the edge of the shadow. Well, you can see immediately that that amplitude at the edge of the shadow, this is now joining to the edge of the shadow. This distance here is obviously half the distance, Z, Z prime, so the amplitude drops by a factor half. It's like in the Huygens Fornell principle, we've just cut out half the wavefront, and so we've cut out half the amplitude, and when we square the amplitude, which is halved, we of course get an intensity which is a quarter. So at least we can immediately understand the first bit of this curve. And now, if you're in the dark region, imagine you start at the origin here and you keep drawing arrows as this curl goes round here. And so let's go to there, to there. You can see that joining this Z to any point, the distance from the origin is getting monotonically larger and larger and larger and larger and larger and so on. So it's a if I join from Z to anything that's in the geometrically dark region, this arrow just gets longer and longer. So the geometrically dark region, of course, I just have a monotonic function here, and it's roughly an exponential decay. It's not exactly, I'll tell you what it is in a minute, but to all good approximations, it's an exponential decay into the dark region. And so, of course, if you go a huge distance into the dark region, you don't get any light at all, as you would expect. But now, when you come into this region, let's say now, we're of course, joining here, it's still getting monotonically, these arrows here are getting monotonically brighter and brighter until you reach a point over here. Hang on, let me just grab another colour. It's getting all a bit horrifically complicated looking. These arrows are getting longer and longer until they reach this point, yeah? But now, as the arrow from here starts to go here, the intensity starts to come back down, yeah? So this point here is precisely this one here, and then as you connect from the origin to this side of the spiral, this connecting point here, you see you've gone round the spiral, you now connect to here, where you've gone through a minimum, but then, so that's this point here that I've just marked is this one here, and then likewise as you keep going round, of course I think once you've got the hang of that, maximum, minimum, maximum, minimum, and so on, and the oscillations get weaker and weaker and more rapid. So that's, if you like, geometrically how you could do the calculation. You could construct a Cornu spiral for yourself purely in the modern way. That's the way you do it. Just whack it onto a computer and calculate the spiral. The way that it used to be done, and again this is just taken from the notes. This is only if you're interested to pursue. This is a bit more kind of tricky, is that you usually express it in terms of a dimensionless variable, and of course it depends on the width of the, the slit, and it depends on the wavelength, and it depends on the distance you are to the detector. But once you've got it in a dimensionless form, you can then find the xy coordinates of any point in that plane by these. So if you like, once you've defined your variable v, which increases monotonically as you increase the distance from the origin here, z is the origin in this, although that's the edge of the geometric slit, you come out. Now they look deceptively simple. The cosine of v squared, however, is not such a simple integral to do, nor is the sine of v squared, and these integrals are called Fresnel integrals. Now again, of course, they're tabulated, and they can be worked out mathematically. So there are two ways in. Mind you, it's not like Fourier transforms. You know, Fourier transforms are quite friendly, whereas Fresnel integral is not something you'd want to meet in a dark alley, sort of, 11 o'clock on Saturday night when the pubs are turning out. They can be a bit brutish and nasty, Fresnel integrals, which is why we're not doing the maths, you'll be pleased to hear. But if you're interested in it, of course, you can calculate this curve exactly by solution of these integrals, and you can always get the overall structure of the spiral. So one of the things which you see, and again, that figure just illustrated three of the points. I went through that. This is edge diffraction. Remember, this isn't circular aperture diffraction. This whole curve is constructed just for a wavefront going past a single flat edge. So it's the absolutely simplest problem you can imagine. And constructing the Cornu spiral for a circular or a rectangular aperture is quite a complicated job, this is just straight edge. I illustrated here the phasor diagrams for successive portions. This was a typical diffraction minimum. That's where exactly that you can see this is the shortest distance to this point. This was the first diffraction maximum. That is the furthest distance you can get away from the origin. So that's the first diffraction maximum. And then when you're inside the geometric shadow, as in case C, this arrow just gets smaller and smaller and smaller, and you get the monotonically decaying function. Now, one of the things that you may or may not have noticed about this weird spiral is that because you've got the arrows always head off, they can never come back to the origin. Like when we got the zeros, like we did that 5-source interference pattern, and the phasor diagram for 5 sources, we did the amplitude for 5 sources, and it kind of went, we had a big thing at the origin, and here we got these zeros at places like phi, a phase angle of 2 pi fifths, because if you've got linear variation around, all the arrows are the same length. So of course, if all the arrows are the same length and have got the same angle with respect to each other, then there is a quite definite, obvious condition when they form a regular pentagon in this case, well, they'll come back to the origin and you get a complete zero, where you get, it's not like here that it's a bit dark, there's absolutely no photons whatsoever, there's zero amplitude at this point. But in this figure, that is not possible. Each of the arrows is at the same angle to each other, but because they're getting longer quadratically, they can't come back to the origin. They end up doing this, weird spiral. That's why it's called a spiral. And so you don't get any zeros in the pattern. So that brings us finally back to figure 70, which I've already kind of used before, which is that if you have, again, a plane wavefront arriving, this is now, you see this pattern here is obtained from what we've just done mathematically by constructing the Cornu spiral for one edge and the Cornu spiral for another edge, and then just bringing them together. Obviously I could say, well, what we've calculated was this situation where we just had a plane wave arriving and half the lecture theatre was opaque and half the lecture theatre was transparent. So the plane wave went past this edge and we calculated the amplitude and therefore intensity as a function of distance from the edge. But of course I could do the same thing. I could make all this opaque and I could keep this region transparent, and then I can calculate, I mean, it's obvious if I can do the calculation for this, I can shift my origin and do the calculation for this other one, and then I just move them together until finally I create a slit of width W. The problem's more complicated adding the waves up because they're spherical waves, but you've still always got linear superposition principle. You know, the Maxwell equations that underlie it all for the electric field vector and the magnetic field vector are linear, so it may be harder maths to do it when you've got your detector close to the origin, but you can certainly superimpose solutions from different cases and use the principle of superposition for the waves. And you can imagine that we've calculated this pattern, which is, well, I'll go back to the actual pattern rather than sketch it. It's probably a little bit more convincing. Now, imagine we get this pattern, and then we bring in another pattern that's like that from this side, where now we've got the little wiggles getting bigger and bigger. Well, what you get in the middle will depend on what you've superimposed. We're superimposing that solution with a solution coming this way, and of course you can, depending on of course we've got the different variables. We've got the width of the slit, the distance to the detector, the wavelength of the radiation. Where it is in detail will depend on those, but you can imagine shifting this pattern across so that this is the middle of the slit, and I add up two minima. In other words, I get a black spot sort of in the middle, a black band in the middle, or I could shift this pattern along so that this is the middle and one of these maxima sits on that one. I could get a bright band in the middle. So, you know, that's why in the end you can end up in Fresnel diffraction. You can even get a dark spot when you shine light through the middle of a circular aperture, which seems at first very counterintuitive. If you shine light through, you think, well, you know, by symmetry, somehow it's all going to add up along the axis, and you're right with Fraunhofer diffraction. But the Fresnel diffraction, you can actually get this black spot in the middle, and likewise, if you have a slit, you can actually get a black band. Sounds odd. You can get a dip in intensity right in the middle of the slit, depending on exactly where you are in this very complex pattern. So I just make a brief board note on that because, it's, as I say, really kind of on the exam type syllabus, what you're expected to know is a near-field diffraction exists, and the Rayleigh criterion of where one goes to the other. The details of this, you can imagine these calculations themselves are quite hard. So I promise I haven't put that on the exam. Question 1 on the exam. Here is Cornu's spiral. Calculate. No, not really. So the irradiance, again, just to emphasize, this is the intensity distribution is shown in figure 76. So that was this figure here. This is the fact. This is the way light goes past a straight edge. It's amazingly, surprisingly complicated. And I say with a modern photon detector, you can actually get literally hundreds of these fringes. Our eye retina is nowhere near sensitive enough for that. But you really do see oscillations in intensity going a long way away from the edge of light going past a wall. But you know, that's a fact. So in the spirit of the Huygens Fornell principle, and again that one I've not made much of, but it's sort of been lurking in the background underlying everything that we've done, this idea of the wavefront. I think it was figure 68 of the course handout. Half the wavefront is removed by the obstacle. So in other words, we're assuming it's semi-infinite, if you like. We've got infinity of opaqueness this way and infinity of transparency this way, and we set an infinite plane wavefront. Half of it gets removed, is removed by the, let's actually put it in brackets, the semi-infinite obstacle. So the amplitude is reduced. So this part of this is the one part of the curve you can calculate, if you like, without doing any kind of deep thinking, because you know that the amplitude's been reduced by a factor half at the edge of the shadow. You therefore know that the intensity's been reduced by a quarter. So the amplitude is reduced by a factor half, and the intensity by a factor 1/4. And again, to come back to these patterns for edge diffraction, again, I scribbled a lot over the main figure, so I'll put this one up here at the moment. So as shown in Fig 79, the intensity decreases monotonically in the dark region. If you're in the shadow region behind the wall, in the dark region, let's just call it, you don't get any oscillations in intensity. This arrow, as you go from the origin to any point in the dark region, shown as figure C here, it's winding away and away and away from the origin, and the arrow just gets longer and longer. So you must get, by looking at the spiral, you get this monotonic decay in the dark region. There are no fringes there, and that's part C of figure 79. And when ZD, and this is referring to the figure, yeah, the Cornu spiral figure, when ZD joins to a variable point in the bright region, we get a series of maxima and minima. And one of the maxima is illustrated here in this figure, because now this is, and in fact this is actually the first maximum, and this is the longest you can make at the arrow from Z to D is this point, because after that, any point on the remainder of the curve is closer to Z than this point. So we get a series of maxima, and part B illustrates the first maximum and minima, e.g. Part A of the figure. So you can imagine, with that kind of amount of hassle to calculate just the diffraction pattern as an infinite plane wave goes past a single straight edge, that if you have Fresnel diffraction close to a circular aperture or rectangular aperture, it gets extremely difficult to calculate. Whereas, you know, in the far field, if you know how to do a two-dimensional Fourier transform, you can, and they're all tabulated, you can get the amplitude pattern in a matter of 5 minutes. but you really have to sit down and, God, do a bit of thinking to get the Cornu spiral. So, because the this is a slight detour, not a detour, but to come back to the Fraunhofer, and so let's just say because Fresnel diffraction is hard to calculate. Let's again, we're not pretending calculating that spiral is easy. We return to the safety to Fraunhofer diffraction, because there's one aspect which I set on one of the problems, next week's problem class, which I think you'd find a bit difficult without a hint. So I'm going to use the last sort of 10 or 15 minutes to look at Young's. So this is, if you like, not really lecture 18, but it's a separate piece on Young's double slit diffraction. So again, physically, it's an extremely simple idea. We've got an infinite plane wave. So what we've done first, we did two-source interference. You might think, oh, come on, Martin, we've done this. We've done two-source interference, and that was on the problem sheet. And we all know that for Young's double slit interference, this hopefully you'll have already done this. The condition for a bright spot is d sine theta equals m lambda. Now we derived that specifically for the case where we had two infinitesimal point sources. So this is what you get if your slit is infinitesimally thin. It now acts as a secondary source. Yeah, so you've got say you shine a red laser on two slits and they're infinitesimally thin. They just act as two completely new sources of waves according to the Huygens Fornell principle, and then they add up. And we've done that to death. You know, we did it for two sources, we did it for 5, we did it for n. In every case, we will get d sine theta is n lambda. So if I had my plane wave coming through here, and I put two sources and their thickness was really dx, or sorry, I've made y this direction usually, dy with x this direction. If they are infinitesimally small, they act as actual point sources of secondary wavelets, and then if I go far enough away from these point sources of secondary wavelets and they've become effectively plane waves, then I've got this very simple addition, and we've done that to death, that d sine theta is m lambda. And often in a Young's double slit experiment, we'll have typically a wave, I mean, again, round numbers, just in a Young's double slit experiment, we've got lambda of the order of 10 to the minus 6 of a metre. Of course, it's, you know, red light is 6 times 10 to the minus 7, but, you know, and we've got the distance to the screen. Let me just make sure this agrees with the notes I'm going to give here. Distance to the screen, capital D, so I've got now, let's just make this a distance screen. Here are my slits, yeah. And here's my distance screen, D. Typically, that distance is of the order of a metre. Typically, my slit separation, small d, the centre to centre of each slit, again, it might be something like 10 to the minus 4, 5 times 10 to the minus 4. But this is for those of you who've done it in the lab, this is, very typical. You shine a red laser on two slits, your screen is about a metre away, your slits are about 10 to the minus 3. So the angle theta is very small in most of these experiments, yeah? So we're entitled to use the small angle approximation. So in a typical experiment, with Young's double slits, we can use sine theta is approximately theta. We've clearly got a reasonable use of the small angle approximation in these circumstances because we've got, you just see the geometry here, theta is of the order of 10 to the minus 3 in radians, so we're clearly going to have the small angle approximation justified, or in other words, d theta is n lambda. Oh, what was the point of redoing all that? We've done that. But now we've done single slit diffraction, and remember each of these slits has got its own diffraction pattern. If I took that slit away and shine the laser through a slit of width of the order of 10 to the minus 3, well, that's precisely what we've calculated, single slit Fraunhofer diffraction. Now, strictly speaking, what you observe is what's called a convolution, you know, in the Fourier transform of the single slit diffraction pattern with the double slit interference pattern. And it's just like in solid state physics, where you get the bright spots in the diffraction pattern is determined by the periodicity of the lattice, but the intensity of the spots tell you about the distribution of scattering length within the unit cell. So basically, having a slit which has got its own, if you like, diffraction pattern, that is what's called the form factor in solid state physics, and the Bragg condition is this one. So the Bragg, if you like, this is like the Bragg, and you'll see it's the same, you know, it's not an accident, this is pretty much the same equation. You've got, now each slit's producing its own diffraction pattern, and what you observe is a convolution. Now if you're a pure mathematician and you're very happy with maths, you'll say, oh Martin, you're making a meal out of nothing, all I've got to do is take the Fourier transform of the double top hat function, and you're absolutely right. However, what I would like to point out, because again it brings home a very important point about not just kind of learning, you know, formulae, is that you've got to be, let me find my far field diffraction view graph. You see, if we're in the far field, the distant diffraction pattern has zeros. Now these zeros are as given here, and you know, people get a lot of confusion. Oh, you know, so this is the diffraction condition for a bright spot, if you like, of 2 infinitesimal slits. So, however, formally, if the slits have finite width, we observe a convolution of the double slit interference pattern with the single slit diffraction pattern. And of course you can solve it outright, because as I travel along this axis, my amplitude, I'm assuming again these are perfectly opaque screens, perfectly opaque screen, perfectly opaque screen, that my amplitude as a function of distance along this axis clearly is just a double top hat function, and I can Fourier transform it, square it, and get the answer. However, this sometimes, I think, ties in better with the idea that you can see it's the periodicity, D, which gives where the spots are, but now it's this new condition. Let's let W be the width of the slit. So I haven't, you know, because I made these notes up as I, you know, like last night, I haven't got any view graphs of them. So small d is the separation of the two slits, centre to centre. W is the width, and big D is the distance to the distant screen. And M is the integer which characterises the interference pattern. So this question that's on the problem class next week is about where are the zeros in the double slit diffraction pattern. So what that means is that if we have some condition where this point, of course we could calculate the whole thing, but again this is to illustrate the principle, where the single slit diffraction has got a zero, exactly where we're expecting, of course, this series of bright spots in the Young's double slit interference, we notice the straight, let's say that's the 0th, 1st, 2nd, 3rd order. For example, we notice there's no 3rd order spot. There seems to be one missing. Well, that's because we've hit a condition where each of the slits has got its own 0 in its diffraction pattern, and that meets this maximum. Once you've got the idea in hand, the maths is quite easy. So the intensity of the spots are modulated by the function sinc squared phi, we know that. Sorry, sinc squared psi, where psi, oops, sorry, I meant to number that equation because I want to put two equations together. So this is the intensity equation for the bright spots. Where psi is equal to pi w sine theta over lambda. And again, remember with this function, so this is where people get confused with the two conditions. This function, the sinc function, which is plotted in effect in figure 64, I've relabeled the axes, you'll see it's got its minima, its zeros are precisely where psi is an integral multiple of pi. So the zeros of this function in phase angle are at pi and 2 pi. So in other words, note that is equal to pi w theta over lambda for small angles. And we'll make this equation 2. Yeah? So we've got move this up a bit. So note that it's the zeros of this function, bless you, occur at psi is equal to n pi. The sinc function, which we get from the single slit diffraction as a function of phase angle, has got its zeros at pi, 2 pi, 3 pi, 4 pi, etc. So, in other words, where do we find zeros of the sinc function? We find zeros of, let's move these up a bit so they're all hopefully visible at the same time. So, i.e. n pi is equal to pi w theta over lambda. I'm just using equation 2, or w theta is n lambda. So this is 3. So by comparing equations 1 and 3, we get the condition for a, let's call it missing spot. It's just like, I don't know whether Sarah did this with you in solid state physics. If you do potassium, I think it's bromide, or is it potassium chloride, one of those simple crystals, because the iron and the two ions have got roughly, not identical, but roughly the same scattering power, same number of electrons, that half of some of the reflections from the BCC lattice are missing. So that's precisely due to this type of condition where it's the distribution of scattering length within the unit cell gives you precisely that form factor runs through a zero where you're expecting to get a Bragg spot and you don't get it. So it's a similar idea, and oh sorry, I have to go on to a separate blackboard to write the equation. So last bit is very simple, that you've got D over W is M over N. In the end, putting all the info together is incredibly easy. Remember, this is the width of the slit, and this is the nth zero in the single slit diffraction pattern. When you compare with this equation, let's try and keep that one in view. This equation here, again, we've made the small angle approximation, so when it became equation 1, that was d theta is n lambda. This is the separation of the slits, and this is the nth maximum in the double slit pattern. This is the nth zero in the single slit diffraction, and this is the width of the individual slit. But if you clearly put those two together, well, if d theta is m lambda and w theta is n lambda, and you divide one equation by the other, on the left-hand side you get d over w and the thetas cancel, and on the right-hand side you get m over n, and the lambdas cancel. So, for example, if the distance between these slits was, let's say, 1.5 millimeters, yeah, and but the actual width of the individual slit was 0.5 millimeter. So, in other words, my d over w is 3. Then the third order spot here will disappear because it's lying on a zero of the single slit diffraction pattern. So that was one and I thought that the reason I went through that was that although once you've got the hang of it, it's relatively straightforward, I thought that would be quite difficult to pick up on your own from first principles in next week's problem class. Don't forget, next week, tutorials and problem classes, make the most of them. Okay, see you later.